what does all this have to do with relativity? Okay, so let's see, does anybody know, that did not know from before, but can anybody figure out based on what we spoke about?
You mean like special relativity?
Without special relativity. We're ignoring special relativity. Now, special relativity is very, 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 very basic. If you think very deeply into space and time, you come up with special relativity. If you think very deeply into electromagnetism, you come up with special relativity. Any measurement that you make, even the measurements that we're talking about, measuring tidal accelerations, need equipment and machines and objects are made of atoms, and atoms has electromagnetism and other forces, obviously. And in order to make all that work, you need special relativity. So the truth is, at some point, you get to special relativity no matter what. But if we're kind of operating in that post-Galilean, post-Newtonian, post-Galilean, pre-Einstein time, because everything that we said now would be pretty much comprehensible to a Newtonian physicist. We didn't introduce anything that's not really Newtonian gravity. We just made some radical suggestions. And we came up with this notion of gravity as a property of the space, which gives rise to relative accelerations. So now, what does this have to do with relativity? Well, if you think about the indistinguishability that we spoke about, that Galileo and others discovered, you have inertial frames that are indistinguishable from each other. So you cannot claim that one is stationary and one is moving at 50 miles an hour and one is moving at 500 miles an hour. All you can see is the relative motion. That's the only thing that could be measured. The one who claims he's stationary measures a relative speed relative to the others, and so do they. They can say that they are stationary. If there's no observable phenomenon in an inertial frame, then the one that you say is moving at 500 miles an hour can equally claim to be stationary, and it's you who's moving at 500 miles an hour. So there is no unequivocal determination that one is stationary, one is moving, or how fast you're moving. They're all the same. They're all inertial states. And the only thing that can be measured is the relative motion of these inertial states. The idea proposed by Newton and expounded on by Maxwell, that if you have an equally accelerating force, so it accelerates everything equally, then things will be accelerated, at least as viewed from outside the system, or that's what we're saying, it's an equally accelerated force. So we're supposing that there is acceleration, and yet you cannot measure this acceleration. The only thing that you'd be able to measure would be relative acceleration. So you can call that some kind of Newton-Maxwell relativity. Now we go one step further. Einstein applied this to gravity, and even though Maxwell actually mentioned gravity as an example, it may be they didn't pursue it further because it's clear that there are these tidal accelerations, and therefore it does seem to be non-inertial. But what Einstein did is he said, no, these frames are indistinguishable from inertial frames, and I'm going to say that they are inertial, and the fact that there is this relative acceleration is going to be what gravity is all about. It's not a disproof of the model. It tells you what the model is. There are locally inertial frames, local inertial frames. That's what gravity is. And when you're in free fall, you cannot tell that you're accelerated. The only thing you can find is this relative acceleration. And it's that relative acceleration that is the phenomenon. And that's Einstein's more generalized form of relativity, as opposed to the relativity of Galileo, or as opposed to the relativity of equally accelerated forces, meaning it's a uniform field, and you can't distinguish any kind of acceleration. He was talking about real cases of gravity, where you have equally accelerated forces, but they're different at each place. And therefore you will observe a relative acceleration. And he was saying, nevertheless, these are individually indistinguishable. And that's a more generalized form of relativity. And there are other ways to arrive at a term, general relativity. You can start with special relativity and generalize it. right? So that's not the only meaning to the term general relativity, just like what I said before was not the only meaning to the equivalence principle.